years I did a quiz every Friday, and then the quizzes were handed back on Monday, and then Wednesday a hint was given for the next quiz on Friday. And that encourages people to come to every class, because at the time, of course, it wasn't being videotaped, so there's no way to find out what the hint was unless you were there.
Sounds like a state machine.
It is. It's a sadistic state machine. So I hope I don't have to go to that, because you ask yourself, what can you do in a 10-minute quiz in a design class? The question has to be really diddly. It has to be a negligibly small chunk of something that you happen to know or not know. And so there's a certain amount of stochasticity to whether you can answer these things or not. I really don't want to go to that. I will. Quiz a week. It's really tedious to grade too, let me tell you. When I was doing that, I spent every Saturday morning grading quizzes.
Will you be lecturing during the final project week?
Will I be lecturing during final projects? Part of the final projects, probably for the first week or week and a half of final projects, we'll still be talking in here. And then after that, we'll go to the lab and be in the lab every morning. Every morning. I'll be there every day. So lectures will be yet more time to work on final project. That'll be something like a week and a half into final projects. Any questions about Lab 2? See, let me also just amplify on this other thing. The only way I can convince the department to still use video note is if you come to class. If you stop coming to class, I kill video note. Department kills video note. Right? So now Danella's heart stops, right? Okay. Questions on Lab 2? How about Lab 3 so far? We've talked a bunch of math, no programming yet. Most of the programming will be left as an exercise to the user, but there's lots of examples online in Lab 3. You better read them. And we'll start talking about them next week, maybe today. But are there any questions about the math? It was strangely silent when I was talking about differential equations last time. I suspect you haven't thought about this for a while. So I expect to hear questions on it. Maybe not today. I want to talk just a little bit about connectors. What we're going to be doing, every lab station has a pair of the cheapest computer speakers I could purchase. And they have on the end, the connection to them is the usual green with standard Windows pale green connector. And the connector is laid out like this. This is supposed to be a very much enlarged version of a 3mm phone jack, so-called. If you look carefully at the end of this connector, there are 3 metallic regions that are separated by insulators. There's a tip, there's a ring, and there's a body. Body. Which one's ground? Always and without fail, every time. Body. Don't ask me again. This one has to be alligator clipped to ground. Which is the tip? Left or right channel? Ooh, that's more obscure. Well, it happens to be the left channel usually. Whether you're looking at the connector this way or this way. So if you put an alligator clip, and you're going to connect to this with an alligator clip, not with twisted wires. You're going to use alligator clips. You all know what alligator clips are, right? Yeah. So you're going to hook on with alligator clips. If you want to get noise out of both channels, then you either have to use 2 alligator clips, or if you're very careful, you can use 1 alligator clip and connect it to both the tip and the ring simultaneously.
Do you have any female jacks in the lab you can just stick on the board?
Yes. By the way, that's referred to as a socket. And between the pulse width modulator output, if you use timer 0, what pin is that? You haven't memorized this yet? Memorize it, folks. What pin is it? That'd be a great quiz question. That's a perfect quiz question because it was in lab 1. No, D7 is timer 2. B3. So we're going to go from B3 through an RC circuit over to the body and the tip of the connector, and we want this time constant. Well, let's see. We're going to have a sample frequency of about 8 kilohertz. So what frequency do you think you ought to set this RC time constant to? With a PWM sample frequency of 8 kilohertz. Well, it better not be higher than 4, right? Because you'll get aliasing. But I would say for safety, you should set it no higher than 2 kilohertz. No, or call it, maybe 10 or 12,000 radians a second. And this resistance has got to be somewhat bigger than the Thevenin impedance of B3, and it's got to be smaller than the input impedance of the speakers, which is a few dozen kilo ohms, or maybe 30 kilo ohms. What? Resistance has got to be a fair amount greater than the Thevenin impedance of port B3, which you know, and somewhat smaller than the input impedance of the amplifier. And so probably, 10K is reasonable. You choose the capacitor so it sounds the way you want it to sound. If you like a nice buzzy sound from an 8 kilohertz alias like you have on an MP3 player, then go for it. All right. Enough of the physical connection. Let's go back now and talk about random number generators. I set up the random number generator, the logic for the random number generator last time, but I didn't write down any code. So we're going to need an unsigned, we're going to first of all define bit 30 as 0x400. And we're going to define bit 27 as 0x0800. And you remember what we're going to build here is a shift register with bit 30 and bit 27 XORed together and then fed back into bit 0. And on every time step, we're going to shift this 1 to the right. Yeah?
Bit 30 is 0x400. How's bit 27? Wait, that's still wrong.
I'm sorry, 4000.
Okay.
Sorry. And we need a couple of character variables, bit 0 and bit 1. And we need a unsigned long 32-bit noise gen and an unsigned car rand, which is going to be the output. We're only going to go for a 7-bit output value. Why 7 bits? Why 7 bits? Oh, because I normalized all of my probabilities to 128. And so the car from 0 to 127 will cover the whole range of probabilities in the Markov matrices. So bit 0 is going to have the value of noise gen ANDed with bit 27 and ask if that's greater than 0, because I didn't want to try and figure out what the number actually is. And then bit 1 is going to be noise gen ANDed with bit 30 greater than 0. Then we're going to left shift noise gen which is, let's see, the weird operator is this, right? Shift 1. That means take noise gen, shift it 1 to the left, and store it back in itself. And then noise gen equals plus equals bit 0 XORed with bit 1. And then rand, the 7-bit output, is going to be, because we're going to cast a car, noise gen and X07F. So that's the entire random number generator. It takes, you have to do 7 shifts to get a new 7-bit random number. You could write that into a function, or you could just run this at high speed in main and assume that we're going to go through main many, many times between the initiation of a new note. New notes are going to happen about 4 times a second, 8 times a second. You're going to run through main maybe 1,000 or 2,000 times a second. And so if you just do a shift operation on the random number generator every time through main, by the time you need to initiate a new note, you'll have a fresh random number. Any questions about this? This is documented, by the way, in a program on the DSP page, which is linked from Lab 3, in which the random noise generator is not used to initiate random notes, but rather to produce white noise, audio white noise. It's the same random number generator, it's just run at a higher speed. I have no clue. I'm guessing it's faster because I believe that the standard way that RAND is written, at least according to Knuth, David Knuth, is as a linear congruent generator, which is an add, a multiply, and an add and a modulo operation, which I'm guessing is slower than this. for a 32-bit multiply. So this uses the kind of bitwise manipulations and the narrow arithmetic capability of the microcontroller very well. Whereas linear congruent generator uses it has to be kind of bolted together. I use this all the time for all kinds of stuff. And, oh yes, I have to say one thing. You have to seed the noise generator at t equals 0 with some value other than 0. Then you don't have to seed it again. But if you pick a seed, you will get the same sequence of random numbers, pseudo-random numbers out, which can be nice for debugging. Questions about this? Okay. Now we need to talk about the last aspect of the signal generation that we haven't talked about yet is how do you generate a sine wave? We've talked about generating exponentials, and that was what worried me, that I didn't get many questions on that. So, and I won't until you start coding it yourself, because that's when you learn everything anyway, not when I'm standing up here talking. But we need to talk now about direct digital synthesis, which is how we're going to generate the sine wave aspects of the musical notes that you need to generate for Lab 3. And the sort of hardware version of direct digital synthesis looks like this, where we're going to take the output of the register, some register, let's call it a 16-bit register in this case. We're going to add something to it, an increment. We're going to add an increment to it and store it back into the register on some clock, which is going to be at the sample frequency fs. We're going to use the top 8 bits as an index into an array whose values happen to be sine x for one cycle. So it's going to be an array which looks like one cycle of sine t. Every time this register overflows, we're going to go through exactly one cycle of the sine wave. So that, and the nice thing about this, the thing that makes it a very natural way to generate a sine wave, is that you can consider this register to be the phase. It's a phase accumulator. In fact, that's what it's usually called, is a phase accumulator. Just as an angle increasing goes from 0 through 360, this register is going to naturally go from 0 through 2 to the 16th and then back to 0 again. So the overflow of the counter is topologically very similar to an angle rotating through 360 degrees. So we can consider it a phase. So what we're going to read out then, we're going to use the top 8 bits of the phase register as an index into the array, and the bottom 8 bits is going to be a fractional degree or a fraction of one step through the index. This allows us to go to lower frequencies where we're stepping less than one step per phase step, less than one array index per phase step at low frequencies. Make sense? I'm here seeing head shaking here. It's not all good. What do you think? All right, so it's really one register. We're going to treat it all as one register. For thinking about it, we're going to say that the top 8 bits is the index, and the bottom 8 bits is a fraction of an index. So if this bit pattern corresponds to 1/2 of one index increase in the sign table. You got a table of sign values, 256 sign values. We haven't written it out yet, but yes, there's an array of 200, size 256 of sign, and you're going to step through that over and over again. And the way we're going to step through it is by merely counting up this register, counting up the register, and when it overflows, we let it overflow, because that's equivalent to wrapping the phase back to 0. Jeremy.
When you say sign values, what range is that in? Is that like, how are we representing the sine wave? I mean, is it?
Well, it turns out that we're going to use 16-bit fixed point multiplied by 127, but that's, yeah, that's scaled weirdly, but we'll talk about that in a minute. Yeah. It won't increment.
It only increments on the first
8 bits.
but the lower 8 just basically makes it so that for multiple iterations you use the same sign value.
It's the same sign value. So the way to think of this is that at high frequencies, you step through the table. At high frequencies, you're going to step through every index in this table. At even a higher frequency, you're going to skip every other index, right? And at even higher frequencies, you're going to skip every fourth index. But at very low frequencies, you're going to stay on this index for a while, for several samples, and then go to this index. And so what you're going to see is something that looks like this. But you don't care, because when you're measuring a slow sine wave, you slow down your oscilloscope. It squeezes everything together, and you can't see the steps. Or put it in terms of Fourier. What is the first non-zero error term in a sine wave that has 256 steps on it? Think about that. So yes, there will be times when you put the same sample out over and over again. There will be times when you skip values in the table, and that's as it should be.
We don't interpolate just to make it that.
Well, there are DDS systems that do interpolate, but we're not going to. So you can ask yourself, what is the maximum possible frequency you can get out of this system? And that is, how many samples per sine wave do you have to have before you can no longer recognize it as a sine wave? Well, 2, right? That's what Nyquist says. Although that's pretty sparse. That's a sine wave represented by that. Oh, that's you know, all right. Well, sure. If you do the appropriate interpolation, sure. But most people would say that if you want some decent harmonic distortion, you need at least 5, or you need at least 8 or 9 points on a curve, on the curve, before you can call it anything like a sine wave. So that'll limit the high frequency. What we're going to do to generate this, now listen carefully, folks. What we're going to do to generate this is we're going to run 2 timers in a strange way. And the reason we're going to run it this way is we want to cut down on the audio artifact. We want to run a pulse width modulator as fast as possible. The fastest we can run a pulse width modulator on this system is 16 megahertz. If we want a 250, if we want an 8-bit pulse width modulator, we have to run it no faster than 16 times 10 to the 6th divided by 256, which is 62,500 hertz. Because we have to go through 256 time steps to get 8-bit resolution on a pulse width modulator. 62,500 hertz is pretty fast. It's way above your audio bandwidth. Even those of you who have very good hearing probably can't hear above 25 kilohertz. Can anybody hear above 25 kilohertz? Does anybody know that they can? The highest I've ever, when I was young, I could do 22 kilohertz. Now I can do 9 on a good day. So if you talk to the back of my head, heads are a low-pass filter, right? Particularly if they have hair, and I don't have so much hair anymore, but heads are low-pass filter. You talk to the back of my head, I can't understand you because the high frequencies are gone. I have to remind my daughter of that sometimes. And the reason I say daughter is that her voice is somewhat higher, and so it's an even worse effect because her fundamental is high-pitched, and so the filtering just gets worse at higher frequencies. Okay, so we're going to run timer 0. Timer 0 we're going to run in PWM mode at full speed. Timer 0 can therefore do nothing else. When it's in PWM mode, all of its other functionality is turned off. It cannot do a compare match. It cannot do an overflow interrupt. It actually can do an overflow interrupt. It can't be used for anything but PWM. Now, 62,500 is fast enough to do some very nice synthesis, but you can't afford to go that fast because you have to do too much arithmetic for this lab. So you're going to sample, so FS is going to be 8 kilohertz, 8,000 hertz, and we're going to time that off of timer 1 compare match interrupt. So once every 8,000th of a second, you're going to update OCR0A, which will change the PWM output for the next 8 cycles of the PWM. If we ran the PWM at 8 kilohertz, you would hear it and you would be sad. It's really annoying. TAs would be even sadder. So, you don't want to run this at, you want to run this at 62,000, which is above audio, but you want to change the value of OCR0A, which sets the PWM value, as often as possible. I suggest starting at 8 kilohertz, you might be able to go to 16,000, as high as 16,000, depending on how you code. So at 8 kilohertz rate, we're going to do the DDS. So the update to OCR0 is going to be do a DDS update, which means calculate a new phase, do a table lookup, and spit the value out to. So we're going to update phase accumulator. Update the phase accumulator and do a table lookup, sine table lookup. and then update OCR 0. Does anybody want an explanation again of how a pulse width modulator makes audio output, analog output? Or is that already clear? If you want it again, I said it once, but if you want to hear it again, ask for it. Otherwise, I'm not going to say it again. Yeah. Okay, so pulse width modulator. Pulse width modulator, as you would guess, is not a pulse frequency modulator. It's a width modulator. So we have a constant frequency output, in this case 62,500. And what changes is the percentage of time that the pulse is high. So we can go from 10% to 50% to 90% perhaps. And that changes. If you were to squint at this across the whole waveform, that would, excuse me, or put differently, if you were to integrate under this curve, you would get a value, an integral, which is proportional to the amount of time that the waveform is high. Said differently, the average value of this signal is 0.9 VCC, the average value of this signal is 0.1 VCC, and the average value of this signal is 0.5 VCC. Therefore, if we change the pulse width modulator and average over one cycle, we have made an analog output whose value is proportional to the duty cycle. And the way we average over one cycle is low-pass filter. A low-pass filter is exactly a exponentially weighted averager. So you want a low-pass filter whose time constant is long compared to 1 over 62,000. So you want the time constant of this low-pass filter we're going to put on the output that I drew before. So tau has to be much greater than 1 over 62,000, but it can't be much. It can't cut off frequencies much below 2 kilohertz. So that puts another bound on it. So it can't be much bigger than 1 over 10 to the 4th radians or so per second. So that says it's got to be between 1/10,000th and 1/62,000th. Yes?
And the calculations for that lower limit with frequency should be in radians, right?
Always in radians.
So we're using our new fixed array value for the sine table to update OCR 0.
Mm-hmm. I haven't gotten there yet, but yes. So now,
The cutoff frequency, we don't want to cut off frequencies based on the audible load. We don't want to cut out frequencies that we
well, you don't want to cut out frequencies that you can hear. Right. Yeah. So, let's say that I want a certain frequency output. Let's say I want a 1 kilohertz output. The only thing I have to set, the only thing I can set, is the increment. How big should the increment be? Because the bigger the increment is, the faster we're going to go through the phase accumulator. The faster the phase accumulator is going to overflow, and therefore the faster we're going to go through this array. At some point, the increment will be correct to get exactly 1 kilohertz. So we need to figure that out. So let's see. If we use a 16-bit counter, then we're going to overflow every 2 to the 16th counts. And if we're incrementing this at, let's say we increment by ones. Let's say we set the increment to 1. Then we're going to overflow in this many seconds. Right? If we overflow in this many seconds, it says then, if we take the reciprocal of that, this is time to overflow. Then the lowest frequency we can generate with an increment of 1, we can generate must be Fs over 2 to the 16th. Reciprocal of that. So that's what? That's in real terms 8 kilohertz to the 16th. That's like an eighth of a hertz or so. It's pretty low frequency. So what's the next biggest thing we can increment the counter by? 2. All right, we can increment by 1. The next biggest increment is 2. So the next biggest frequency is 2 times Fs over 2 to the 16th. And in fact, in general, the frequency output, this is the sine wave frequency out, is equal to Fs over 2 to the 16th times the increment. Or in other words, the increment is F out times 2 to the 16th divided by 8,000 if it's 8 kilohertz. So that's just 8.192 F out. So that says that if we want a kilohertz out, if we want a kilohertz output sine wave, we set the increment to 8,192. Of course, we could use a 32-bit system. At 8 kilohertz, that gives us an awesome resolution. It's like a millionth of a hertz resolution, which could be useful for some cases, but not for music, I don't think. Any questions? So I see lots of pointing at things and talking, which means to me that there are questions.
That 8.192, that's the actual, like the 8 would be the represented by the upper 8 bits and the lower 8 bits. Is that
Well,
in the register?
that's bits in the register. That's the increment that you're adding to the register every time through. That's actually getting close to the maximum frequency you can generate with this system at 8 kilohertz sample rate. If you want to generate a higher frequency, you need to go to a higher sample rate. It's really easy. The nice thing about direct digital synthesis is that it's really straightforward to program. 2 lines of code per sample. One to increment the accumulator, the other one to do the table lookup. So you can write a lot of them. You can have a lot of them in a high-speed loop and add together and make lots of sine waves, which means means you can afford to add together a lot of sine waves, which means you can do Fourier synthesis. Now, as a detail, let's talk about the sine table here. No questions on this. In years past, I've had the students. The feeling is, wait a minute, this is too easy. There's something I don't understand. It's too easy. In fact, it's just easy. But it's easy to get confused on also. And one reason it's easy to get confused is we have lots of different samples going on here. We're sampling a sine wave. We're sampling the pulse width modulator as a sample. Timer 1 is producing yet a different sample rate. So we have at least 3 different sampling schemes going at the same time that you have to sort of keep in the right hierarchy of understanding. Right? You have to keep track of what's going on. So typically, that's a homely sine wave. Goes from +1 to -1, and from 0 to 2 pi. But we need this. We need to scale this so that it looks more like this. And we're going to use 8-bit fixed point. We're going to therefore store this as -127 to 127 with an index of 0 to 255. And so that tells us right away how to initialize the array. Table with index I is going to have a car value, C-H-A-R, a car value of 127.0 times the sine of 6.283, that being close enough to 2 pi for all practical purposes, times float I, times float I divided by 256.0. Now, I suggest when you look at the online examples, you look at the FM modulation examples, the FM synthesizer examples first, because those are the ones I wrote last, and they are therefore most like what I've talked about. The ones I wrote a year ago are different. Look at the FM synthesis stuff first. Any questions? So, building this table is time-consuming, but you do it once. It's then reused, the same table is reused for all of the synthesis you're going to do. Oh, but wait. This table could be anything. It doesn't have to be sines. It could be something that looks like that. You wouldn't bother with writing a table which looks like a sawtooth because that's just I is equal to the output. Right? That you wouldn't bother having a table for that. But you could make a a triangle wave this way, you could make a wave that goes like this. If for some reason you wanted it. You could have any shape table you want in there, which actually is useful for special effects, for making interesting sounds. Because whereas a sine wave is, of course, going to be one pure harmonic, if you put a... Oh, here we go. Let's think back to signal processing. If we have a discontinuity, what does that say about the spectrum? The spectrum must go as 1 over n, and it can't drop off any faster than that. So there's going to be a high frequency tail, 1 over n in frequency. Now, what about the symmetry of the wave? You remember probably that if you have a wave which is symmetric about the x-axis, that you have only the odd harmonics. This has all of the harmonics in it because it is asymmetric around the x-axis. So having a waveform which is a sawtooth is a good way of making a complicated, rich sounding utterance with lots of harmonics in it, which just not coincidentally is how your vocal cords work. Your vocal cords open slowly, slam against the stop, and slam shut, right? And so you get a sawtooth pulse of air out at around 100 hertz, mas or menos, and because you're producing a sawtooth, then you have lots of frequencies to drive the resonant system, which is your throat. And because there are lots of frequencies, there will always be a frequency near the resonance of your throat so that you have a loud sound coming out. So, you could experiment with that. You could have a table which is a sawtooth or some sort of almost sawtooth. Oh yes. So now let's say we have a triangle wave. That's symmetric about the x-axis so that it only has odd harmonics, and it only has first order discontinuities. It has discontinuities in slope but not in value, and therefore its spectrum drops off as 1 over n squared. These are just good things to memorize. You need them for the rest of your life. Drops off as 1 over n squared, and so it's a mellower kind of tone that comes out from that kind of waveform. The only way to get a handle on this is to start playing with it in lab. The only way to get a handle on it, like any other thing you're going to deal with in life, is to start writing a program and make it work. You can write it in C, you can write it in MATLAB, doesn't matter. But you've got to write out this direct digital synthesis stuff. You've got to play with the sine tables, listen to what it sounds like. Because it's the only way to figure it out. Any questions?
So here the idea is the higher A bit in that register, right? The index I in the table is the...
Yes, the index here will be the high byte of the phase register.
And then the lower A bit, how is it exactly used here?
It overflows into the high order bit. The only way the low order is used is to overflow into the high order.
That's the only use for that lower A bit. That's just kind of add
It's
resolution.
It adds resolution to the frequency, exactly.
Okay, okay.
Good way to say it. Let's get out of here.